There we go. Heard the beep. I'll begin with a word of prayer. So, Dear Father, we thank you for this day. Again, Lord, thank you for these students, that we all found parking spots somehow and or walked from our dorm, you lazy people. Help us to learn a lot together today and just to glorify you, learn what we do. In my prayer, Lord Jesus. Amen. Yes, I parked at the top of the parking garage. I feel like I drove a mile to work and then another mile inside. Like, I must be doing it wrong. I'm like, it's like, I felt like a never end. I'm happy to find a spot. But anyway. So I forgot to take attendance last time, which is bad. So if you were here last time, I mean, I'm not so organized as to like take points off if you miss 10 classes or something. I mean, attendance is its own reward. If you make a habit of not coming to class, I'll get you on the test. I mean, it's just going to happen. And the same for homework, right? I'm not recommended homework. If you just don't do any of it, it'll be very, very obvious to me when I grade your test, right? I mean, so, well, anyway, we talked about that last time. Let's go on. So I want to talk to you about another example here. And so I like this example because it gives us a sort of look at how methods are related, and it allows me to talk a little bit more about the general idea of an integrating factor. I mean, the integrating factor method is what we presented last time to solve a problem like this, right? But there's sort of a more, so I want to look at this from a new perspective. Here's the new perspective. So if I had more common sense, I would have written this before I wrote the example. Sorry. What's written cannot be unwritten. So here's the new perspective. If m dx plus n dy equals to 0 is not exact, all right? And parenthetical comment, how would we know that it's not exact? What does it mean for it not to be exact? There doesn't exist an f such that this is the total differential of f, right? You can't write this as df of some given function, two variables. Now, the simple test for that is just that partial m, partial y is not equal to partial n, partial x, right? If that's the case, if that if that condition is not met, then you know it's not exact, all right? In other words, you can't write m dx plus n dy as df, all right? Well, here's the good news. If this is not exact, then for nice enough m and n, that's my cop-out because I forget the conditions on m and n here. So if you're a math major, I'm sorry, but if you're an engineering person and you're not super excited about all sorts of technical, nuanced mathematical statements, I mean, there is some condition which is still needed on m and n in order for what I'm about to say to be true, but in practice, it's almost always fine, all right? Then there exists I such that im dx plus in dy equals to 0 is exact. Right. This thing I'm telling you is called FAFSA theorem. Pfaff was the research advisor of Gauss. Pfaff's other students include Mobius. Like, you've heard of Mobius strips? So, anyway, this basically says, more or less it says that most differential equations, like pretty much all first order differential equations, if you write them in Pfaffian form, there's some other function you can multiply it by, and it'll make it into an exact equation. So this means that the method of exact equations is quite general. Now here's the rub. They're like, well, why don't you just teach us exact equations? Well, the trouble is actually finding the integrating factor for an arbitrary differential equation is more difficult than solving it. So it's kind of a useless comment from a sort of abstract calculational perspective. But it's fun to try to put this Pfaff's theorem in practice for this equation. All right, so let me show you. Let's try to work out Pfaff's theorem for the linear ODE. All right. So dy dx, in other words, let's try to find an I such that this becomes exact. And let's try to understand why this is not exact to start with, right? So let me work it out over here. We have what? We've got dy dx plus py minus q equals to 0. Multiply by dx, we get py minus q times dx plus dy equals to 0, right? So this is the first order differential equation. Let me call it star. What did I do? I just rewrote it in terms of its so-called Pfaffian form. So identify, what do we got here? What's our m, what's our n? This is m, right? If you look in here, there's a 1. See it? Right there. So that's n. Now what are we assuming about p and q here? They're functions of x alone, right? I didn't say that, but that's assumed, right? Let's assume they're continuous. Maybe differential. Anyway, okay. I'm trying not to get into that stuff. All right. So what do we need for this to be exact? Is that an exact equation? Why or why not? What happens when we calculate partial m? Partial m, partial y is what? It's p. Very good. And what's partial n, partial x? 0, right? Oh, well. So the only way this could be an exact equation is if what? P is 0, right? So if p is 0, what's this equation become? It just becomes dy dx equals to q. So, yeah, we could solve that, right? You integrate both sides. I mean, that actually is an exact equation, though, is what this says when you sort through it. Okay, so, but generally speaking, when p is not 0, that's not an exact equation. So let's look for I. So look for I such that I times py minus q dx plus I dy is equal to 0 is exact, right? Now this I is, generally speaking, in principle, is some function of two variables, right? In the abstract, you can think of I as being some function of two variables. But, so, generically, I would be a function of x and y, but to make life easier, try I is just a function of x to start with, right? We do this a lot in here. We form a general guess, and then we add some extra condition on it to try to work out the math more efficiently, right? We're looking for a solution. We don't have to give an account for all possible solutions, right? It's kind of like looking for a wife or a husband, right? You can add conditions, right? But if you add too many, you might not find them, right? Like maybe insisting that they also like Naruto. Is that step too far? I don't know. Sorry. No one watched Naruto anymore. What am I talking about? For me, it's okay. Oh, man. The fuzzy. Hey, I love doing this. That's what it sounds like in their ear, right? Oh, come on, stupid thing. Well, anyway, where was I? Wasting time, mostly. Okay, so if this, now this is our new m, right? And this is the new n. What's the exact condition we need? We need partial m, partial y equals to partial n, partial x. What's that give us? Partial m, partial y is what? It is just y is the right kind of idea, but the y differentiates to 1, right? So IP, yeah. It's a good thing my children are not here. They'd be snickering. Partial n, partial x, well, I is just a function of x, so that's in fact di dx. So what's that give us? That gives us di over I is equal to p dx, yeah. Integrate both sides. What do we get? We get natural log absolute value I equals to integral p dx, right? Plus a constant, fine. So I is equal to, you know, plus or minus e to the c, e to the p dx, like that. So just set that initial constant to 1. What did we find? What did we say the integrating factor should be last class? Exactly that. So in fact, this integrating factor that we show you for the linear differential equation is a special case of a more general idea, which is that given an exact equation, you might be able to find some other function that multiply it, an inexact equation. You might be able to find some other function that when you multiply by that other function, it becomes an exact equation. Yep. Yes, the function has to be different from 0. And again, there are some conditions that have to be met for m and n, like maybe differentiability, or they can't both be 0, something like that. I just forget. Since I forget, I don't want to try to state it carefully. But there's a proof of FAFSA theorem in a math stack exchange question that I asked, or my brother asked like 5 years ago. It'd take me a while to find it, but it's not too hard to prove. Anyway, I think this is very interesting because this formula, I mean, we showed it works last time, and that's neat, right? But this actually is some kind of derivation of it, which is kind of precious to me. All right, anyway. There's a larger discussion of so-called special integrating factors in the book. I don't usually teach that deeply, so I'm just going to go on, all right? So the next order of business is substitutions, all right? So I'm going to spend most of today talking about substitutions. And in so doing, we're going to get more experience with the 3 techniques that I introduced last time, all right? Because pretty much every substitution problem, what ends up happening is we make a substitution, and then it becomes either a linear differential equation or a separable equation or an exact equation, all right? So let's see how that goes. Work a few standard examples for you guys. Here's a good starting one. Suppose we're trying to solve dy dx equals to x plus y minus 6 squared. All right. So let's see here. So how do I solve this? Well, what I do is I make a substitution. So basically, there's just this mess, right? So it seems like if we just call this thing v, that might help us figure out how to solve this. Maybe if we could write v in a marker that actually works, it'd be helpful. I don't know. That's sort of better. All right, I guess. All right, let's go back to the black. So if that's v, whenever we make a substitution, we have to think about the algebraic aspect of it, but also the differential aspect of it. So if I'm trading my dependent variable y for a new dependent variable v, right? I'm going to have a dependent variable v, independent variable x. I need to figure out what dv dx is as it relates to dy dx. The way to do that is just to differentiate the substitution. So like dv dx 1 plus dy dx, and the derivative of minus 6, 0. So, okay, so I've got that. I put both of these into the differential equation. What does it give me? Well, what is dy dx? dy dx is actually what? It's dv dx minus 1, right? If we solve this for dy dx, we get dv dx minus 1. So that's dy dx. And what's that equal to? V squared, right. So we get dv dx is equal to 1 plus v squared. And then but now we're back to one of our favorite methods, right? Because we can separate variables here. So I got dv over 1 plus v squared. You guys are all shadowing me in my calculus 2 this semester, so you know how to integrate this, right? Inverse tangent of v is equal to x plus a constant. I'm kidding. We just worked it out yesterday, though, but it's kind of funny. No, 2 days ago. Yesterday was race day. Very exciting. Very, very exciting. Let's see here. So v is the tangent of x plus c, right? Take the tangent of both sides, but what was v? Of course, at that point, we have an implicit solution, right? I want to find the explicit general solution. What is it? Looks like 6 minus x plus the tangent of x plus c. Right? At which point a comment is in order, I think. Like, okay, yeah, I mean, if you want a function, you add x to it, you subtract 6, you square it, and that gives you the slope. I mean, obviously, y equals 6 minus x plus tangent of x plus c is your man. Right? I mean, anybody could guess this as a solution to that, right? No. But through relatively little work, we found this really quite sophisticated solution. I mean, algebra and calculus are so powerful. We should appreciate this sometimes. Without the notation that we enjoy, algebraic notation and calculus, it would be something that only a genius could understand even, much less write. You might be a genius, but I'm certainly not. I mean, it's not that, it's just amazing to me what we're able to do at this point in history. So, that's example number 1. Example number 2. This is an example of what's called a homogeneous differential equation. Suppose you got dy dx equals to y over x plus 1 over y over x minus 1. Make sure I got my, yeah. So the reason this is called homogeneous is if you have something like dy dx equals to just, some function g of the ratio y over x, then that kind of differential equation is called a homogeneous differential equation. This word homogeneous is used for a lot of different contexts. That's its less common use, but anyway, fun fact, it's called homogeneous. But, I mean, if we scale x and y by the same thing, like if you take your y and replace it with 2y, and you take your x and replace it with 2x, that function g is invariant, right? So that's some kind of symmetry of the differential equation, the scale invariance of y and x at the same time. All right, enough about that. So what do we make v? We make v y over x. Now, you could just differentiate v like I did last time, but I think it pays off to do just one algebra step before I do that. So this says y is xv, right? I'd rather differentiate x times v, because then I'll get what dy dx is immediately. And, well, you guys know, you know it, you love it, the product rule. So there you go, x plus x dv dx. So I have everything I need to change the given differential equation. Let me make it famous. There we go. It's a star. Yeah, sorry. You guys are it's a hard crowd. Hard crowd. So v plus x dv dx. So So it looks like I'm doing puppets for cubbies this semester. So I have to invent 3 voices. One for Cubby, the Cubby Bear, the other for the Lovey Lamb or something, and the other one for like a dog. Some of you have had experience with this back in the day? No? I'm talking about Cubbies is a Bible club for little, like 3 to 4 year olds. I'm not sure I have 3 appropriate voices. Like, I think like a robot voice. I can't use that, I don't think. I mean, I don't know. This is going to be... But I was thinking if I get good at this, I might start like using puppetry to introduce definitions in my other classes. It might make it more memorable, you know? -1 over v minus 1. Then I can write a paper about it and publish it in an education journal. Wouldn't that be awesome? Let's see here. Sorry. I'll try to set the sarcasm to a slightly lower level. Let's see here. X dv dx equals to v plus 1 over v minus 1 minus v. So, yeah. What do we do with that? You're like, common denominator. Okay, I'm with you. So this is v plus 1 minus v times v minus 1 all over v minus 1. Right? Common denominatoring. And then what do you got here? You got yourself a minus v squared, right? This gives me a plus v, so plus 2v. And looks like we've got a plus 1 divided by v minus 1. The minus sign is troublesome. I just don't like that minus, so I'm going to pull it out if you don't mind. So we got x dv dx equals to minus, parentheses, v squared minus 2v minus 1 over v minus 1. I wonder if I made a sign error here. I've got that feeling. Is that factor? I mean, you're like, well, everything factors. I know. But does this factor nicely? I don't know. I don't. Not nice. No, right? No. It's yeah. If that was a if there was a plus 1, it'd be nice, right? But it's not. Okay, but on the other hand, the integration is actually not that bad. Let me show you. So this, we can separate variables though, right? So this gives me v minus 1 dv over v squared minus 2v minus 1. And I'll just keep that minus dx over, I'll put the minus on the other side just to be different, right? There you go, integrate both sides. So can you do the integral on the left-hand side? You should be able to, actually. Even Calculus 1 students should be able to do that one. How do I do the integral on the left-hand side? Telling you Calculus 1 students can do it is a huge hint, because the only integration technique they know is what? Partial fractions? No. No, I don't. I mean, we can all dream of a world where Calculus 1 learns partial fractions. NC State. But, for example. But, no. How about u substitution? Let the denominator be u. Then du is 2v minus 2 dv, aka 2 times v minus 1 dv. Ha-ha! So, yeah. This is actually 1/2 integral of du over u equals to minus the integral of dx over x. Integrate both sides, we get 1/2 natural log the absolute value of u is equal to minus the natural log, the absolute value of x, plus a constant. And then we have to unsubstitute. Ay, 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 ay. V squared minus 2v minus 1 equals to minus the natural log, the absolute value of x plus a constant. And what was y? What was v? Yeah, y over x. So this is the natural log of the square root of the absolute value of y over x quantity squared minus 2y over x minus 1 close absolute value equals to minus the natural log, the absolute value of x plus a constant. Here you go, implicit solution, yes. What's that? Did I? Oh, yeah. Excuse me. I'm sorry. Let's put the, yeah. So rather than square rooting, what I should have done, right, is I should multiply by 2, which would put a 2 over here, right, which would make this, what would that make this? And, well, find 2c, but we can call it c bar, same stupid thing. So that's actually natural log 1 over x squared. See, the absolute value of x squared, guess what? X squared. And plus a c bar. And then, as King was saying, just exponentiate both sides. And that gives us y over x, quantity squared, minus 2 times y over x, minus 1, equals 1 over x squared times a constant. Right? And then if you multiply this by x squared, you get y squared minus 2yx minus x squared equals to a constant. And there you go. That is another implicit form of the general solution, which maybe is to be preferred. It's a little bit easier to kind of look at. I mean, you can solve that for y, I suppose. Could you? Could you solve that for y? Could you, would you? Would you want to? I suppose I could. It's a quadratic in y. I could solve for y, right? So y is equal to 2x plus or minus the square root of 4x squared plus 4x cubed divided by 2. Oh, the k. I'm ignoring the k. That's if k is 0. So sorry. There's a k. Anyway, let me stop. It's not interesting. You could solve this. I mean, put k to the other side. It's a quadratic equation in y. You could solve for y. Let me stop. The larger point here, right, is if you have a differential equation that's written in terms of ratios of y over x, this substitution tends to be pretty effective. All right. Let's look at another. Example 3, here we're asked to solve y prime plus xy equals to xy cubed. So what's this kind of like? It's kind of linear, right? I mean, it's not quite linear though, because it's got this y cubed, right? A linear differential equation has derivatives and the dependent variable appearing linearly. If there's a square, a cube, a square root of the dependent variable, it's not linear. So this is nonlinear. but it's kind of almost linear. So what you do when you see one of these sorts of problems is you make a substitution. The substitution that you can make is z equals to y to the minus 2. Right? And the reason we do that is because of this term. Right? If instead of having y cubed here, you had like a different thing, you could kind of follow the same pattern. I have a general prescription for how to solve. These are called Bernoulli differential equations. So remark 2.46 on page 28 of my notes gives you the general scheme. So that will tell you what to do for similar but related problems. Okay? Now I'm going to focus on this problem here though and show you how it works out. Because what I'm trying to do is make sure that we all understand how to make a substitution on a differential equation, right? If you're confident about your calculus skill, you didn't really need to learn anything from me, right? Because I'm just telling you, make a substitution, take a derivative of it, be careful to do the chain rule, and then plug it in. That's all I'm saying. There's no kind of extra secret handshake or something. I don't know any of those. Yeah. Differentiating this is kind of a drag. You know, I don't know what to do. I guess I'll just differentiate it. I've forgotten how to be clever here. So let's just calculate. dz dx is, what is it? It is minus 2 y to the minus 3, right? dy dx. So we could solve for dy dx. What does it give us? Looks like minus 1/2, right? I have to multiply by y cubed, right? And then I've got dz dx, yeah? So far so good, right? Now, what I'll do is I'll take that, right, and I'll put that in for this, right? So I've got minus 1/2 y cubed dz dx plus xy equals to xy cubed. Now what I want to do is change y's to z's. In view of what? We're making the substitution z is equal to 1 over y squared, right? Seems like I should, before I do that, right? It's helpful to do what first before I do that? It would make that job a lot easier algebraically, just looking ahead. Can you see what I should do first to make life easier? What's that?
Take a y away.
Take a y away. Divide by y. Divide by. I like to divide by y cubed. That sounds lazy to me. 1/2 dz dx plus. I mean, if you just battle through the laws of exponents, you'll get to the same thing. If you're good at laws of exponents. But this is easier. So x 1 over y squared, right, equals to x. Oh, this is wonderful because now, what is 1 over y squared? Yeah, that's just z, right? I got this pesky minus 1/2 out here, but we can take care of that in the next move, right? So we get dz dx minus 2xz equals to minus 2x. So a Bernoulli equation, all right, if you make the right substitution like the one we just made, which is basically always, so if this is instead n, you let z equal to what? This one we looked at n equals to 3. We got minus 2. So what's that? And minus n plus 1, actually. But yeah, you get the right idea. Just multiply by minus 1. Yeah. So that's what we generically do. But when you make that substitution, what happens with the Bernoulli equation is it changes from a kind of linear equation in y to a straight up linear equation in z. See, that's a linear first order differential equation. This we can solve by the integrating factor method. Let's do it. Let's solve this thing. So we got dz dx minus 2xz equals to minus 2x. All right. So I got to identify mind your p's and your q's, right? Nobody says that anymore. What am I saying? Minus 2x. My grandparents have both gone on to be with the Lord, but that was an expression from their generation, I think. Mind your p's and q's. Let's see here. They also had some other meaning for physics. Anytime I'd say I studied physics, they'd start giggling. It's like, what's wrong with you people? Anyway. Okay, so my integrating factor, exponential, integral of minus 2x dx, also known as e to the minus x squared. Yeah. So multiply both sides of your equation by e to the minus x squared. That should get us where we want to go. E to the minus x squared dz dx minus 2x e to the minus x squared z equals to minus 2x e to the minus x squared. Whew! It sure is handy that they put that 2x over there, isn't it? Because if that had been just about anything else, we would have been up a creek. I mean, there is not so many things that you can multiply by e to the minus x squared and successfully integrate. Now, think. Don't be like me last class. Actually think through it. Does this make sense, my next step? If I differentiate e to the minus x squared times z, does that actually get me back up here? Chain rule. Yeah. Reverse product rule. That means that I calculated the integrating factor correctly this time. Not like that sign error last class, right? And on the other hand, of course, still minus 2x e to the minus x squared. Now we integrate both sides. That gives us e to the minus x squared times z is equal to the integral of minus 2x e to the minus x squared dx, also known as e to the minus x squared plus a constant. Thank you, Calculus 1. Make a u equals minus x squared substitution. Or just guess. If you differentiate what I wrote down, clearly you get back to the integral, integrand rather, so that's an antiderivative. Solve for z, right? What's z equal to? One plus c e to the x squared, yeah? So multiply the green equation by e to the x squared, the natural enemy of e to the minus x squared. They obliterate in a flash of light and give you the number 1. And you get z equals 1 plus c e to the x squared. Of course, we're not done yet. We're trying to find y as a function of x, right? What's z, though? Ah, 1 over y squared, yeah? So what's this give us? This gives us y is equal to plus or minus 1 over the square root of 1 plus c e to the x squared. And there you go. It's about time we solved an initial value problem. IVP. assume y of 0 equals to minus 2. If I give you that extra piece of data, that means that there's not going to be a c in the solution, right? And also, there's not going to be a plus minus in the solution. Repeat after me. Repeat after me. If I'm given initial data, there will not be a plus minus in my final answer. I must commit. I must choose a sign. You don't have to repeat that. But so like, I don't know, this is just something that you guys struggle with is you get really good at this kind of stuff, and then I give you something extra like, okay, now find the constant that makes it minus 2. And then I'll see things like y equals plus or minus. You find the c, sometimes correctly, and then there's still plus minus in the answer. You can't, you got to make a choice. It's either plus or minus for this kind of problem. There do exist problems which have more than one solution fitting initial data, but this is not one of those. So, okay. Spiel over. Minus 2 equals 2. So what do we choose, plus or minus here? You have to put in minus, all right? Otherwise, you can't get y as negative because the square root is by definition positive. Minus 1 over square root of 1 plus c, yeah? E to the 0, 1. So, you square both sides and you get 4, 1 over 1 plus c, aka 4 plus 4c equals to 1. So 4c equals to minus 3, so c is equal to minus 3/4, I think. But I could be wrong. I like minus 3/4 because then I get the square root of 1/4 in the denominator, which is the square root of, which is 1 over half. And 1 over 1/2 is 2. So I like that, yeah. So in fact, this has solution y is equal to minus 1 over the square root of 1 minus 3 over 4 e to the x squared. And there you go. Hey, we solved our first initial value problem. You remember this moment in time. What's that? I
mean, like, there's a y equal to 0 is also a solution.
is what, did I choose one that's not? Please tell me. So you said y equals 0 is also a solution? But y of 0 equaled just 0?
Yes. But, yeah.
Oh, but that doesn't have minus 2. Oh, you're just saying that there's another solution I'm missing. Oh, okay, yeah. I was worried that you had also found another solution that has y of 0 equal minus 2. It's like, oh no. That usually happens when I make that kind of speech. You know, I have the misfortune of choosing that one example. All right, no, yes, you're right though, you guys. If you plug in 0 back into the original equation, that also works, right? That solution is extraneous to our derivation here, right? Because we start out with z is 1 over y squared, right? Y equal to 0, no can do, right? So yeah, y equal to 0 is another, it's an extraneous solution. Depends on whether or not I remember to take off the point. You remind me though, right? No. Okay, so Bernoulli equation. I guess I should actually write that down, Bernoulli. You know who the Bernoullis were? I mean, this is the old family. I mean, I think it was before Newton or around the time of Newton. I mean, we're talking 17th century, I think. There's like 3 of them. There's a father and 2 brothers. They all kind of, it's sometimes I don't know which one did what because they all kind of borrow from each other. It's a mess. Let's see here. All right, let me move along here. One more example. Now, actually 2 more examples. One will be quick. One will be slightly less quick. Well, I mean, then I have a different topic I'm talking about. It's not the end of class. Don't get your hopes up. See here. So suppose, is there a question? No? All right, so by the way, there's an obvious question to ask here. So you expect me to like know what substitution to make for like all problems involving a substitution? No, I don't expect you to know that. I will pretty much tell you, make a v equals to blah substitution on the test, because I simply do not assign enough problems to expect you to acquire that skill. You'd need to see a couple dozen problems, right? I think. Or I just need to talk about pattern recognizing, and I just don't think it's that interesting. I want you to be aware of the technique, and also to be aware that there's so much more out there. I mean, I'm showing you just a select couple of substitutions. There's dozens of these things. Specific to particular subdisciplines, there's going to be some special substitution you make for an application. There's tons and tons of different differential equations out there. I'm just trying to show you the way of thinking, not all possible solutions. There's just too much to show you. For these first order problems, in contrast, I will show you how to solve any nth order constant coefficient differential equation. Like no exceptions, our method's general. It's just these first order differential equations, they have all kinds of different flavor options. I mean, because we look at nonlinear problems, and so there's all kinds of crazy stuff that can happen. Anything you learned integration-wise can come up, you know, because we're always integrating. So there's a lot of scary stuff here, if you don't know calculus too. So I try to get past it so it's not making too much of the semester scary. All right, let's go on here. Example 4. What if you were trying to solve this? Y prime prime plus y prime equals to 0. This is a second order differential equation, but we can solve it using first order techniques by something called reduction of order. Okay, so what's reduction of order say? It's actually a substitution idea. We let v equal to y prime. We make a substitution of velocity. Right? What's that differential equation become in terms of velocity? Well, now it's not so scary, is it? I mean, that we can solve. In fact, that's dv dt, right? Equals to minus v, so dv over v equals to minus dt. Integrate both sides. Natural log absolute value of velocity equals to minus time plus a constant. Therefore, the velocity is equal to some constant k e to the minus t by the usual algebra steps. Then I suppose we need to integrate again to get back to y, right? So this is equal to what? It's equal to dy dt. Oops. That's equal to dy dt, so then what do we get for y? How about some constant, right? Minus k e to the minus t. And there you go. That's the general solution to this second order differential equation. Why are there two constants in a second order differential equation's general solution? Does that intuitively make sense to you? Like, here's a simple one. What if I solve y prime prime equal to 0? You can solve this, right? This gives me y prime equals to c1. Integrate again, I get y is equal to c1t plus c2, right? What are c1 and c2? c1 is y prime of 0, and c2 is y of 0, right? So the meaning of c1 and c2 are initial position and initial velocity in this case. Now, generically speaking, the constants could be more jumbled up. They might have not directly that meaning, but essentially fixing the constants c and k in the problem above, that fixes the initial position and velocity of the solution. So for a second order problem, we expect that there will be two arbitrary parameters in the solution because it takes both position and velocity to fix motion for for something that's governed by a second order differential equation. Because it's basically like doing two integrations. Each integration you do adds a constant, right? And those constants are not related. If I had a third order differential equation, it's kind of like integrating 3 times. So I expect there to be a C1, a C2, and a C3 in the general solution. All right? That's my, I guess you should say, the intuitive understanding of it. Anyway, this is reduction of order, which is kind of a neat trick. But what's the probably most important differential equations you saw in physics? Maybe or maybe you didn't cover it. It depends on how Dr. Skambordis is feeling in a given semester. Sometimes he'll spend a couple weeks on simple harmonic motion. Did he do simple harmonic motion if you guys took his course? Talk about springs. What differential? What is spring? What's the spring law? Minus kx, right? So if we have ma equals to minus kx, I should really say y here because we've been using y in that role, okay? Y is our position. If I put m equal to k equal to 1, right? That gives me y prime prime equals to minus y, right? And that brings me to example 6, which I want to try to figure out how to solve. How do we solve y prime prime plus y equals to 0? Obviously an important problem because springs without friction, right? Reduction of order. If we try the same thing we did in the last example, example 4, it's not really very successful, is it? Because this is v prime, but this is, it's not v, it's y, it's right? So we go back and we do is we let v be dy dt, right? And so a is equal to y prime prime, right? It's also equal to dv dt. And then we make that, we use that trick I did last time. So we rewrite this as dy dt dv dy. In other words, v dv dy. That timeless equation trick we did. And once I do that, see, then I can trade my acceleration term for something that's manageable in terms of v and y. See, so that becomes v dv dy plus y equals to 0. So I trade out time for position, is what I do to solve this one. And once I do that, I think we can solve this one by what? What method would you solve that differential equation now that we've come to it? Separation of variables, right. So what does this give us? v dv is equal to minus y dy, right? Oh, no. Separation of variables. We've done too much separation of variables. No. Exact equation. See, this is v dv plus y dy equal to 0, right? If you look at this, this is the differential of 1/2 v squared plus 1/2 y squared, which gives me joy to write because I'm just saying that the total differential of the energy is 0. In other words, the solution is a level curve of energy. Fun physical comment for you. But anyway, solution, 1/2 v squared. Well, we can get rid of the half, right? Just absorb the half into the constant. So what we got here is v squared plus y squared equals to a k. That's we're going towards a solution. We want to actually solve for y though, right? What's v? What was v? dy dt, yeah. So now, this gives us dy dt, quantity squared, right? Equal to what? Equal to k minus y squared. So that tells me that dy dt is equal to plus or minus the square root of k minus y squared. And then I can separate variables. So I know you guys are like, I want to separate variables. Well, just be patient. We'll get to it. K minus, see, we did it. Here it is. Plus or minus dt. Integrate both sides. Again, since you guys have been stalking me in calculus 2, you're well remembering this integral as being an inverse sine. Right? Inverse sine. So this is inverse sine of, I believe, I mean, you got to like factor the k out. That gives you a y over k quantity squared. So you make a y over k substitution. I may be missing a factor here. You guys tell me. If we differentiate that, what's that give us? Yeah, this 1 over square root of 1 minus y over k quantity squared times 1 over k, right? Times, well, I'm differentiating with respect to y. Then I multiply that through. That gives me, oh, I'm sorry. If you guys don't mind, the easiest way for me to fix this, it's kind of obnoxious what I'm about to do. You'll forgive me. Square, 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 no square. Yeah. See, because then when you bring the k inside the square root, it becomes k squared, and you get k squared minus y squared, which is what we had. So, yep. And that's equal to plus or minus t plus a constant. So finally, we get y over k is the sine of plus or minus t plus a constant. In other words, y is equal to k times the sine of plus or minus t plus a constant, which you might as well write as a times the sine of t plus some phase angle, where a is the amplitude. Fine, I mean, that plus or minus depends on the initial phase. I mean, well, the plus or minus can get wrapped up into the phi. Appropriate choice of phi can turn a sine into minus a sine. What's that? I'm trading the k for an a. There's a lot going. There's a fair amount of trigonometry. I'm saying the integral of this is that. I don't think so. No. But my point is, if you differentiate this, oh, you think there's supposed to be 1 over k here in the integration? I don't think so. But when I differentiate this, I get 1 over 1 minus that quantity squared chain rule multiplies by 1 over k. The 1 over k supplied by the chain rule multiplies back in to give me this.
Yes, but 1 over k is constant.
Yeah?
Well,
We can talk after class. I think I'm right here.
well, I remember this, the modular solution of that differential equation is sine kt plus some phase, not just t.
Yeah, but it's just sine t here because I'm not doing an arbitrary one. I'm doing k equals to 1.